So we saw the standing wave in the video. And the wave is here and the wave is here, even though there's a node in the middle. And so the 2s orbital is like the second harmonic of a standing wave. It has a node. It has a place in the middle where it's zero. The probability is zero. And the 3s orbital is going to have two nodes. So here are illustrations of these. So this is a quarter section of the spherical orbital, and we see that it has nodes in it. So if we look at the, what am I looking at here? If we look at the probability density, it's better to look at the radial probability. We see that there's zero probability at the nucleus, and the probability rises and then it falls again. There's the node, and then it's greater out here. So the analogy with the standing wave is not perfect by any means. I'm trying to get rid of this down here. It's just going to have to stay there. There we go. But it gives us an idea. So this would be like freezing the standing wave. And then in the 3s orbital, there are two nodes. In the 4s orbital, then there's going to be three nodes. Questions?
So, I understand the counting the wavelengths, but what exactly is the harmonic?
The harmonic, when you look at a standing wave on a string, is you increase the frequency of the wave. You double it. The second harmonic is double the frequency, and that causes a node to occur because it cuts the wavelength in half.
Okay.
Oops. So this is a more solid geometric description of an orbital. But it's important that we understand that the s orbital is not a balloon. It's not a hard shell that we're going to find the electron inside of, and the electron's just zinging around inside of there. This is just easier to represent than showing that dot diagram of it. But every principal energy level has one s orbital. And in those principal energy levels, the 1s orbital is always the lowest in energy. So in the Electron Hotel, which I realized I called it wrong. I originally named it the Quantum Hotel. Doesn't that sound fancier? In the Quantum Hotel, the S room on each floor is the cheapest room on that floor. Okay, it's the least expensive. And electrons like to be in the lower energy states whenever possible. P orbitals, the first energy level, n equals 1, doesn't have a p orbital. But the second energy level and everything above that has p orbitals. There are 3 p orbitals on each level, and they point in different directions. And they have a node at the nucleus, and then the higher ones, just like the s, are like harmonics of a wave, and they have additional nodes. So here's pictures or graphs of p orbitals. The hard description here, the hard picture reminds me of balloons, right? And so here's more of the probability map, the dots, right? And so there's a node at the nucleus. The electron is not found at the nucleus. The probability is greater over here and over here. And so then we wonder, well, how can the electron be here and be there without going through the nucleus where the probability is 0? Because it's a wave. So if we look at this, doesn't this look like a standing wave on that string? It does. And so the probability is a maximum in this region and in this region, and there's no probability in there. But we saw that the wave was on both sides of the node. So because the electron behaves as a wave, it can be on both sides of the node. But if we freeze it, then we see that it's on one side or the other when we make it a particle. So there's one p orbital along the x-axis, one along the y-axis, and one along the z-axis. So there's 3 of them. In the quantum hotel, the p sublevel, the room designated p, like the 2p room, has 3 beds. And so they're going to be perpendicular to each other. The radial probability goes like this for the 2p orbital. 0 at the nucleus, goes up and then goes back down as you go distance away from the nucleus. Any questions? The d orbitals, there's 5 in each subshell. You have to get to n equals 3 before you get any d orbitals. And there's 5 of them. 4 of them are going to be aligned in different 3-dimensional planes. And then the 5th one is just along the z-axis. Most of these have 4 lobes. The p orbitals had 2 lobes. So here are pictures of these. So this looks like, kind of a doubled p orbital, right? And so, we could imagine that this is the standing wave. It's kind of a flower shape, right? And so there's one in the YZ plane, XY plane, DXZ plane. This one is in the same plane as this one, but it's tilted. It's moved over a quarter of a turn so that the lobes of this one and the lobes of this one are not on top of each other. And the 5th one's just plain weird. And these shapes come from the mathematical equations that are describing the electrons. Questions? I'm not going to make you draw d orbitals. I'd like you to have a clue what they look like. You should be able to draw s and p orbitals. Those are pretty simple. A ball and 2 balloons, right? And there's the f orbitals. There's 7 f orbitals. And these are even crazier.
Don't even show us.
No, I'm going to show you. There they are. Aren't they nice?
I like the first one.
Yeah, isn't this one cool? It's like that 5th d orbital, but just kind of split. It's just crazy. So the first one, the second one, and the third one are actually the same, but they're just oriented differently in space.
And those where the electrons go?
Yeah, so the pink volume describes where there's a large probability of finding an electron.
How do scientists test that if it's such a microscopic scale?
Well, you can't look at it, right? Where they've developed equations to describe the probability of finding an electron, or the probability of an electron being within a region. And the equations that they've come up with match up with all of the experimental data that we've been able to get. And so the quantum mechanical model of the atom, like any other theory, cannot be proven correct. But nobody's been able to prove that it's incorrect. We were able to prove that the Bohr model of the atom is incorrect, because it only works for hydrogen.
So we just assume it's correct because we can't prove it.
We have to assume that it's correct because we have no proof that it isn't. That is science. That's how science works. And so, we come up with a hypothesis and we test it and test it and test it and test it, and nobody can prove it wrong. And sometimes that goes on and on and on, and it never gets changed. But sometimes technology comes along and gives us new insights to show that, oh no, there was a problem with that. But to the best of our knowledge, the quantum mechanical model is correct.
So in this chapter, is there not a lot of math? It's just knowing what this stuff is?
There's not a lot of math in this chapter, that's correct. There's a little bit. We did the calculation of energies. So The reason that we're not doing the math for this is because that's a whole nother course called physical chemistry. And you can't study that without a foundation of calculus. So, yeah. So we're telling you enough that we can explain what the electrons are doing and how that affects the properties of the atoms. So it's kind of like a teaser for PChem, which probably most of you will never take. It's okay. So these orbitals, these funky shapes, are determined from mathematical wave functions. And those wave functions can have positive or negative values. Just like when we looked at the standing wave on the string, the wave goes above the middle line and it goes below. And there are also nodes where the wave function is 0. So the sign of a wave is called its phase. And orbitals, being wave functions, can interact like waves do, and they can interact and interfere constructively or destructively. So if the waves are in phase, they will interfere constructively, and if they're out of phase, they'll interfere destructively. And that's going to become important when we talk about bonding later on in the chapter. So here's the illustration of phases. In the s orbital, you're going to see one phase at a time. It'll either be positive or it's negative. In a p orbital, though, in the 2p orbital, one of the lobes has a positive phase and the other has a negative phase. And that becomes important later when we look at how these two orbitals, one from one atom and one from another atom, can interact with each other to create chemical bonds. So we've looked at all these crazy shapes, like balloon art gone insane. And yet we're always drawing atoms as if they're spherical. How can they be spherical if they're made up of all these wacky little shapes? Well, what happens is if you superimpose all those orbitals, you do get something that's roughly spherical. So they basically add up to be roughly spherical. So we think of atoms as being spherical.
And those stack.
Well, they don't really stack, but they overlap.
Okay.
Yeah. And that's kind of crazy.
Electrons collide.
That kind of is crazy to think about, too. There's the end